Let's study 10th Standard ICSE Physics, Chapter 12A, Radioactivity. First, let's understand the basics of radioactivity. That is, what is an atom and what is the structure of an atom. In the planetary model of an atom, we have the entire mass of the atom concentrated in the central nucleus with electrons revolving around it in shells. That is not an accurate picture, but at school level, it's a good model to start studying some properties of an atom. The nucleus has some particles called nucleons, which are protons and neutrons. Protons are positively charged and neutrons are neutral. They need not be in the same quantity in the nucleus. For example, here in the sodium atom, you see that there are 11 protons and 12 neutrons. So the total mass number is 23. 23 is the mass number because that's the number of protons plus neutrons. We don't add the number of electrons while calculating the mass number because electrons are almost massless. Approximately 2000 electrons mass, total mass, will be equal to the mass of just one proton. The atomic number, on the other hand, which is a more fundamental property of an element, tells us the number of protons, and in a neutral atom, that is equal to the number of electrons. The electrons are arranged according to certain rules of duplet and octet, but that's a part of chemistry, and radioactivity is a totally nuclear phenomenon. The electrons do not affect radioactivity. The neutron is extremely small. It is of the order of 10 raised to minus 15 meter, whereas the atom is far bigger compared to that. It's of the order 10 raised to minus 10 meter or 1 angstrom. Nevertheless, still the atoms are so tiny that no one has directly observed one, even with the most powerful microscopes. The shells are called K, L, M, and so on. Now, if you look at the symbol of an electron, proton, and neutron, it's written like this. One electron's charge is negative 1.6 into 10 raised to minus 19 coulomb. That's a very small charge and it's negatively charged. Protons have the same charge, but it is a positive charge. But note here, it is also a very tiny charge on just one proton. So even though the masses are completely different, proton is much heavier than an electron, but the charge is same, and that's why an atom is neutral, because the number of electrons and protons, that is the amount of negative and positive charge, is exactly equal. A neutron has zero charge and its mass is almost the same as a proton, but it's slightly heavier. It could be slightly heavier. Now, if there is any chemical reaction in which the atom participates, that will affect the number of shells, the number of electrons in its shells, but it will never affect the nucleus of the atom. The atomic number or mass number, neither will change due to chemical reaction. But in a nuclear reaction like radioactivity, there will be a change in the atomic number or the mass number or both. Also, a chemical reaction requires lesser energy compared to a nuclear reaction. Now, what if instead of 12 neutrons, there were 13 neutrons? Then the atomic number would still be same, 11. That's the identity of sodium. But the mass number would increase. It would change to 24. It would still be sodium. It would still have the same chemical properties because the electronic configuration will be the same. But it would be slightly heavier. It will have slightly different physical properties. So such atoms with different atomic mass number but the same atomic number are called isotopes. Now here we see example of isotopes. The usual hydrogen found in nature has atomic number 1 and mass number 1. That is, it has 1 proton, no neutron, and 1 electron. But there are some isotopes like deuterium and tritium which do have neutrons, due to which the atomic number doesn't change, the chemical properties don't change, but the mass number changes, so the physical properties are slightly different. Note that these heavy isotopes are not stable. When the number of protons and neutrons are almost equal, then the atom is more stable. But if the number of neutrons is far greater than the number of protons, then the atom is not stable. It can decay. It can give out some radiations to become a stabler atom. That is the cause of radioactivity, instability of certain nuclei. Tin has the largest number of isotopes. It has 10 isotopes. Many isotopes are called stable isotopes. They do not decay, but there are some unstable or radioactive isotopes. For example, in uranium, the atomic number is 92, but the mass number is 235 or 238. In both the cases, the number of neutrons is far greater than the number of protons. See, number of neutrons can be easily calculated by the formula mass number minus atomic number. And when the number of neutrons is far greater, then the nucleus is unstable. So that is why uranium is a radioactive substance. It does not have any stable isotope. On the other hand, carbon, which has 3 isotopes, has a stable isotope as well as unstable isotope. Carbon 14 is unstable. In fact, it is useful in carbon dating. That is finding out the age of a substance like a fossil. Next, we have isobars. Isobars are places where isotopes can hang out. Well, actually, they are atoms of different elements which have the same mass number but different atomic number. So it's like the inverse of isotopes. An example is sodium and magnesium. They have the same mass number, 23 and 23, but atomic numbers are different, 11 and 12. So it has 11 protons and this has 12 protons. This has 12 neutrons and this has 11 neutrons. So the number of protons and neutrons are mirror images of each other. Since they are mirror images, they are called mirror isobars. Finally, we have isotones. They are atoms having different number of protons but the same number of neutrons. That is, their atomic numbers are different and mass numbers are also different. Number of protons are different but number of neutrons are same. This has 12 neutrons and even this has 12 neutrons. Now let's understand what is radioactivity. It was discovered by Henry Becquerel once he left some uranium salt on a photographic plate which was wrapped in black paper so that the photographic plate is not affected by any light. Later he saw that the photographic plate was still affected. That's possible only if the salt of uranium is emitting some kind of radiations which can pass even through black paper. The light rays and other electromagnetic rays known at that time could never pass through that. That's when he realized that he has discovered some new kind of radiation. He called it Becquerel rays. This is how radioactivity was discovered. Now, understand that even though uranium was in a compound form, it was a salt of uranium, not pure uranium, still it showed the radioactivity phenomenon, because even if radioactive elements are combined with some other elements chemically, it does not affect radioactivity because radioactivity is a nuclear phenomenon. Any physical changes like change in pressure or temperature or any chemical change such as heating, freezing, magnetic electric fields, oxidation, reduction does not affect radioactivity at all, because these chemical changes will affect the electrons, the outermost shells. They can't affect the nucleus, and radioactivity originates in the nucleus. And this property in which a substance disintegrates by spontaneous emission of radiation. Spontaneous means it can happen unpredictably. We can't predict when the radiation will be released. We can only give probability of that. So such substances are called radioactive substances. Now, all isotopes of all the elements above the atomic number 82, that is after lead, are radioactive because in their nucleus the number of neutrons is much more than the number of protons. So lead is the heaviest stable element. Yeah, there are some unstable isotopes even lighter than lead. For example, I just told you that carbon 14 is an unstable atom. Radioactivity is a nuclear phenomenon. Now, if you do this experiment in which we have this radioactive substance giving Becquerel rays in a straight line, we keep it in a lead box because lead would make sure that these rays are not emitted in any other direction, which could be quite dangerous. And if we have a magnetic field around it, or an electric field rather around it, then we will notice that some rays are deflected towards the positive plate, some rays are deflected towards the negative plate, whereas some rays are not deflected at all. This means that these radioactive radiations are made up of 3 types of rays: alpha, beta and gamma, out of which beta rays are made up of negatively charged particles That is why they are attracted towards the positive plate. And the alpha particles are made up of positively charged particles. That is why they are attracted towards the negative plate. And the gamma rays are not made up of any charged particles. In fact, now we know that they are not made up of particles at all. They are just a part of the electromagnetic spectrum, just like light and X-rays are. That is why they are not affected by any electric field. Now, the direction of their deflection in the magnetic field can be understood only with the help of Fleming's left-hand rule, which you will study in chapter 10. It tells us that if the direction of current is in one direction and the direction of magnetic field is in the other direction, in which direction will the force work? That is something we will study in chapter 10, so no need to worry about it now. But just remember that if the magnetic field is inwards, means it's going inside the book. You see, magnetic field is always from North Pole to South Pole. So imagine the North Pole is on top of the book and South Pole is behind the book. Then the rays are going inwards. In that case, beta is towards the right and alpha is towards the left. That's all you need to remember for now. Now, beta particles are negatively charged. And now we know that actually these beta particles are nothing but electrons. And these alpha particles, which are positively charged, are actually helium nuclei. That's right. A helium atom has 2 protons, 2 neutrons, and 2 electrons. But if you remove the 2 electrons, then we have a positively charged nucleus with atomic mass 4. You see, 2 plus 2, 4. And atomic number 2, of course. That is called an alpha particle. It's a doubly ionized helium atom. That's what an alpha particle is, actually. Now let's compare the properties of alpha, beta, and gamma radiations. Alpha particles, as I said, are a stream of positively charged particles, doubly ionized helium atoms. Don't say doubly ionized helium nucleus. If you want to say helium nucleus, then just say that. Beta particles are nothing but electrons, but surprisingly, these are not the electrons from the shells of the atom. If you remember, radioactivity is a phenomenon which happens at the nucleus. So these electrons are actually emerging from the nucleus. That is why they have a special name called beta particle. Now you may wonder, how can the nucleus have electron? Well, it doesn't. See, what happens is that during radioactive decay, since the number of neutrons in the nucleus are too much, some neutrons, like this one, can decay to form a proton and an electron. Here you see the atomic number is 0 because we can see that it has no charge. This has 1 charge and this has negative charge, so atomic number is 0 or is -1, negative charge. And mass number is 0 because it is almost massless. Now why are we calling this a beta particle? Because this is not an ordinary electron emitted from the shell of the atom. It is being emitted from the nucleus. The neutron has decomposed to form a proton, and this beta particle is shot out of the nucleus at a great speed. But that doesn't mean that the neutron is made up of proton and electron. It's just that the neutron can decompose to form 2 new particles which were not there previously. That's explained in detail by quantum mechanics, but we just have to know that that's how the beta particle originates. Gamma rays are electromagnetic radiations. They don't have any particles in them, although you can call photons as their constituent particles. Alpha particles travel at the speed of 10 raised to 7 meters per second. That's really fast. That's like 10% the speed of light. Beta particles travel at 90% the speed of light. And gamma radiations travel at the speed of light, in vacuum, however. Their rest mass is 4 times the mass of proton. The value in kg need not be studied. 4 times the mass of proton, yes, if you remember, it is made up of 2 protons and 2 neutrons, so approximately 4 protons mass, or 4 AMU. Electron's mass is negligible. It's just very small compared to even 1 proton. Gamma radiations have no mass because the rest mass is 0. We should mention rest mass because when they travel at such great speeds, their mass increases. Yes, mass is never constant. It depends on your speed. The faster you travel, the more is your mass. But the increase in mass is significant only at very high speeds. And this is related to Einstein's theory of relativity, and it is related to Einstein's equation of E is equal to mc squared. Now the charge of an alpha particle is 2 times that of a proton because the neutrons don't have any charge. Beta particle has a charge of an electron and gamma radiations have no charge. They don't have any wavelength per se. Gamma radiations have a range of 10 raised to -4 nanometers to 10 raised to -13 nanometers. That's the same as 10 raised to 4 nanometers, by the way. That's the approximate range of gamma radiations. Alpha particles are deflected less in an electromagnetic field compared to beta particles. Gamma radiations are not affected at all. But why are beta particles deflected more? If you see here, clearly beta particles are deflected more than the alpha particles. Well, that's because of their mass. Alpha particles are so heavy, their momentum is so much that it takes time for them to be deflected. Whereas beta particles are so light that they can easily be deflected because their momentum is very less. The ionizing power, well, since alpha particles are slowest among the three, they will be able to ionize the medium through which they pass. For example, if alpha particles are passing through air, they will knock off the electrons from the shells of the air molecules. That is, they will ionize the air, so they have maximum ionizing power. Beta particles have ionizing power, even they will knock off electrons and create ions in the medium, but its ionizing power is less than that of alpha particles because they travel quickly, so they don't disturb as much as the alpha particles disturb the air molecules. Gamma radiations are so fast that they hardly ionize the medium through which they pass. Now, alpha particles, since their speed is lesser compared to beta and gamma, their penetrating power is small. That is, they can pass through 3 to 8 centimeters of air and then they are blocked. So they can pass through a very thin page, but a thick paper will just block them. Beta particles have more penetrating power because their velocity is high. They can travel up to a few meters in air. They can be blocked by 1 millimeter thick lead or 5 millimeter thick aluminium. So they can penetrate through our skin and damage our internal organs, whereas alpha particles are blocked by the skin, so they can only cause skin rashes, they cannot enter our body. Gamma rays are extremely powerful. They can penetrate and travel a few hundred meters in air. They can be blocked only by thick lead sheets or thick concrete blocks. That is why nuclear reactors and nuclear facilities have a lining of lead or thick concrete blocks to prevent the gamma rays from escaping, because these gamma rays are very dangerous. They can just pass through our body, even through our bones, by the way. They're more penetrating than even X-rays. They can even cause cancer in us. They can cause immense damage, and the least damage is caused by alpha particles, of course, because they're blocked by skin. Now, let's understand what happens when an alpha particle is released. This is a general equation. Let's take an example to understand this. There is a uranium atom. Its atomic number is 92 and mass number is 238. It's unstable. It would like to be more stable. It would like to lose weight so that it's back in the game. It would release an alpha particle, which is nothing but a helium nucleus, by the way. So it has released 2 protons and 2 neutrons. Now, if 2 protons are released, its atomic number will decrease to 90. And if 2 protons and 2 neutrons, that is 4 nucleons, have been released, its mass number will decrease to 234. So remember this, whenever there is an alpha emission, the mass number of the daughter nucleus is 4 less than that of the parent nucleus, and the atomic number is 2 less than the parent nucleus. Now let's talk about beta decay. That's something quite tricky. If a carbon-14 atom releases a beta particle, that is an electron, by the decay of the neutron, then what will be the product here? Let's understand this. 1 neutron, so this has 6 protons and 8 neutrons, okay? 8 neutrons are there and 6 protons are there. One of the neutrons decayed to form a proton and a beta particle, that is electron. See here, neutron becomes proton and electron. That's a radioactive decay. The beta particle was emitted away, that's gone. So now what is left? 7 neutrons are left. There are only 7 neutrons left because one of them decayed. But the number of protons will increase now. It will become 7 because one of the neutrons decomposed into a proton. So the atomic number has increased by 1, that is, it is 7. And the mass number is 7 plus 7, 14. So you can see the mass number remains the same, 14 is 14. But the atomic number has increased by 1. So that's what happens whenever a beta particle is released. The atomic number increases by 1 and the mass number remains same. Atomic number increases by 1 because the number of protons is now 1 more, but the number of neutrons is 1 less. So the total remains the same. You can see that by these radioactive decay, elements are being transformed. This is called transmutation of elements. Imagine if we could convert any element into gold. Well, but that will be so expensive that it's not worth it trying to achieve that. Next, gamma emission. Well, gamma emission is an emission of an electromagnetic wave. It's an emission of energy. There is no particle being released, so there will be no change in its atomic number or mass number. It's just that after the alpha emission or the beta emission, some extra energy also remains in the parent atom. That extra energy is just released as gamma rays. Remember, alpha and beta particles cannot both be released at the same time. It's always one at a time. Although gamma rays can be released along with them. So this is a summary of the changes which happens when alpha beta particles are released. Some numericals can be asked based on this. Now let's understand the uses of radioactivity. Radioisotopes, that is the isotopes with atomic number greater than 82, that is after lead, and even some lighter elements have some radioactive isotopes. For example, cobalt 60, carbon 14, potassium 40, even they are unstable because the number of neutrons are far greater than the number of protons. So they have many uses. For example, in medicine, the cobalt 60 releases some gamma rays which can help to kill cancer cells if properly used. Yes, gamma rays can cause cancer and can also be used to cure cancer. Next, the salts of some weak isotopes like radioactive sodium chloride. They are used as tracers. You see, once some of the sodium chloride is injected into the blood, and they will continuously give out rays which can be captured by some device. So as it passes through the various parts of a body, the machines and the computer can help us understand the internal organs, whether they have some tumors or blood clots, etc. A similar method is also used to understand what's happening inside a plant body. How do we know that water rises in a xylem or food flows through a phloem? Well, we use tracers. These tracers are nothing but radioactive substances which give out rays, and those rays are not visible to the naked eye. We need machines to track them. Another use of these tracers is in a process called radiocardiology, which helps us to understand the functioning of the heart. Gamma rays are also used to sterilize or kill the germs on bandages, dressings, syringes, etc. It's a very cheap and reliable way. Next, alpha particles are used as projectiles. That is, we can shoot alpha particles on things to study their nuclear properties, etc. And as I said, in radioactive carbon dating, it does not mean going on a date with carbon. It simply means that by calculating the percentage of carbon-14 in any substance like a rock, etc., we can know how old is it, hundreds or thousands or millions of years old, because this carbon-14 is unstable, so it will decay. And we know the rate of decay. It's called the half-life. For example, if I have 1 kg of carbon-14, I know that after a particular interval of time, let's say after 5 years, it will become half kg. But what is shocking is that radioactivity is a spontaneous phenomenon, which means that out of 1,000 carbon-14 atoms, I can predict that half of them will decay after a fixed interval of time. But which particular atoms will decay and which ones won't decay is absolutely unknown to us. One wonders how they kind of communicate amongst themselves to decide who will decompose and who won't. And what is even shocking is that out of 1,000, let's say 500 have decayed after, let's say, 5 years. Then after another 5 years, they will be halved again. So out of 500, exactly 250 will decay. It's totally statistical and probabilistic, but we need not worry about it in school syllabus. This was just some information which you will study actually only in college physics and nuclear chemistry. Coming back to uses, industrial uses, radioisotopes can be used as a fuel for atomic energy reactors. They help us to produce electricity. They can be used by engineers to prevent charge formation on machine parts due to friction. So this will prevent any sparks in the machines. And it can also help us to decide and control the thickness of paper, etc. Because we know that particular particles like alpha particles have a fixed penetrating power. So by shooting it across paper, etc., we can know if the paper is thick enough or not. Now there are some sources of harmful radiations. First of all, some radioactive fallout from nuclear power plants. Sometimes there is a leakage or an explosion in the nuclear power plants which can release some radioactive fallout. Some examples have to be studied. For example, USA, Ukraine, the Chernobyl disaster, and Fukushima in Japan. These accidents were disastrous, and that area is now uninhabited. Nobody lives there because the radioactivity persists even till today out there. And you know, these rays can cause cancer and other diseases in our body. Another source of radioactivity are nuclear wastes. After the fuel rods in the nuclear power plants have been used up, they need to be disposed, but they're still radioactive. Although we can't use it efficiently anymore, they do give out rays still, so they have to be disposed very carefully. They can't be just dumped in open garbage. We'll have to put it in some lead containers and bury it deep inside the earth or in some unused mines. so that they don't harm us for centuries to come. And of course, there is something called cosmic radiation in X-rays. You see, from space, many rays are being emitted by various stars and black holes. Yeah, but some of them reach the Earth's surface and pass through our body. We can't help it. This cosmic radiation is small enough that we don't have to worry about any harmful effects. But what are the harmful effects of such radiation? Well, there are some short-term effects like diarrhea, sore throat, loss of hair, nausea, that feel like vomiting, diarrhea is loose motions. And there are some long-term effects like leukemia, blood cancer, or cancer of any part of the body. And there can be some genetic effects. Your DNA may be damaged by these radiations, and if the DNA is damaged, then it can cause cancer, or your future progeny, your children, may be defective. That's what happened in Hiroshima and Nagasaki after the nuclear bombs. Many people died, but those who survived, their DNA was damaged, and then the generation after generation, defective babies were born because of these rays. That's why pregnant women should not be exposed to rays, especially X-rays. They use sonography instead to understand the inner parts of the baby. There are some safety measures which we can take if you're working in a nuclear power plant. First of all, the nuclear reactor should be shielded with lead and steel walls. It should be in a strong concrete structure which can withstand the earthquakes. There must be a backup of cooling system for the reactor core. So if there is a case of failure of one system, at least a backup can work and prevent the core from overheating and melting, which is what happened in the Chernobyl nuclear disaster in Ukraine many decades ago. And the people should wear lead-lined aprons and lead-lined gloves. They should use lead tongs to handle radioactive materials. And they should have some film badges, of special film badges, which change their color based on the amount of radiations they have been exposed to, so that they can be aware of whether they are still safe or they have been exposed to too much radiations, in which case they should take a break. Also, radioactive substances should be kept in lead containers. And while disposing them, the casks should be made up of lead. It should be disposed deep underground or in useless mines. Now, as I said, there are some background radiations which we cannot stop from entering our body. There may be some internal sources like carbon-14 and potassium-40, which is there in our body in very small quantities. And there are some external sources. For example, there are some radioactive elements in the earth called radon-222. In the atmosphere, it may be there. There are some solar radiations. So the total background radiation is not more than the permissible limit. So it's safe enough to go out of the house. You need to read all the solved examples, but you need to solve question 11, 13. These two numericals have to be solved. But no need to write so much theory here. That is just an explanation. Let me solve a few numericals so that you would know what it is all about. Let's look at this question here. The mass number is 238 and the atomic number is 92. If it releases an alpha particle, what will be the mass number and atomic number now? Well, if you know alpha particles, so this will become 234 and atomic number will decrease by 2, so 90. Then it releases a beta particle, so atomic number always increases by 1, but the mass number remains the same for beta particle if you remember the rules. Again a beta particle, then again the atomic number will increase to 92 and the mass number will be the same, 234. So you see, S and P are the same element, 92, 92, but the mass numbers are different because now they have different number of neutrons, although the proton number is the same. So that's it, sum is over. This is a more challenging sum. Now here we'll have to go reverse. If alpha particle is released here, means the mass number here should be 4 more than this, so it should become 176, and the atomic number will be 2 more than this, that is 71. Even here alpha particle is released, so this will have mass number 4 more than this, so that's 180, and the atomic number is going to be 73. And if a beta particle is released, then the atomic mass number is the same always, 180, but the atomic number will be 1 less, 72. So I did the reverse things compared to this. So here you can see that P and S are actually isotopes, and here X and X1 are isobars, same mass number and different atomic number. Let me do one more sum for your benefit. A nucleus emits 2 alpha particles, so it's double ticked. You'll have to solve it in the numericals book. 2 alpha particles and 1 beta particle to form a nucleus, which is this. Find the atomic number and mass number of X. That is the starting point here. Well, if 2 alpha particles and 1 beta particles are released, Now you just have to remember these two formulae. Number of alpha particles is the original mass number minus new mass number upon 4, and number of beta particles is 2 times the alpha particles minus brackets original atomic number minus new atomic number. How I derived these formulae? Well, let's see if you can figure it out. Now if I use these formulae in the given sum, then it's easy to find the answer. Number of alpha particles is given as 2. Original mass number is unknown, we have to find it. New mass number is given as 2 to 2 upon 4. Cross multiply it, solve it, get the value of A. Next, second formula, number of beta particles is given as 1. 2 times alpha, alpha they have given as 2, minus original atomic number unknown, new atomic number is given. Open the brackets, solve it, get Z alone, which is 88. So that's the final answer. So this was the original atomic number and the original mass number. At the 11th solved example, you can either solve it with the formulae which I just showed you, or you can use logic like they have to find out the number of alpha and beta particles. You see, first of all, we see that if the mass number has decreased by 32, that means 8 alpha particles have been released, because 8 into 4 is 32. If the mass number has decreased by 32, means 8 alpha particles have definitely been released. But if 8 alpha particles have been released, then the atomic number should decrease by 16. See, whenever 1 alpha particle is released, atomic number decreases by 2. So if 8 alpha particles have been released, atomic number should decrease by 16. But atomic number has decreased by only 10. That means atomic number decreased to 16. It became 76. But then the atomic number again increased by 6 and reached 82, even though the mass number remained the same. What causes an increase in atomic number? The release of beta particles. That means after 8 alpha particles were released, 6 beta particles were also released. So read this to understand the logic better, although I've just explained that. So either you can use logic, although you don't have to write all this in exam, only the final answers are enough. Try to use these two formulae in this sum to calculate the number of alpha and beta particles.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.